Once I know the underlying stochastic process is the birth death process, and that too it is a finite state, and also it is irreducible. So, therefore, all the states are positive recurrent. So, I can solve the PQ is equal to 0 and the summation of PA is equal to 1. I can get the steady state or equilibrium stationary probabilities. So, if I solve this system of equation with the summation of PA is equal to 1, I will get the PIs, where PA is in terms of initially P naught and the P naught is 1 divided by this. So, this result is available in this following paper. Here the lambda is nothing but lambda 1 plus lambda 2 and mu is nothing but mu h plus mu 2, and those mu i's are n times mu, and A is nothing but rho, that is lambda by mu here, and A1 is lambda by mu, because the birth death process with the birth lambdas and after that lambda 2, therefore, you have a different expression for 0 to n minus g and n minus g to capital N, you have a different expression for the PNs. So, this is the steady state probability. Once you know the steady state probability, our interest is to get the dropping probability and blocking probability. Dropping probability is nothing but the handoff calls are dropped because of the system size is full. That means all n channels are busy. That means the system, when the system size is in capital N, then the new calls are dropped. Therefore, the dropping probability is equal to the probability that n customers in the system. Here n is nothing but the number of channels, capital N is the number of total number of channels, all are busy. Therefore, the P suffix n will be the dropping probability. Blocking probability is related to the new calls. So, the new calls are blocked, it is not even enter into the system whenever the number of available channels are less than or equal to g in the system. Therefore, when the system size is from n minus g to capital N, the new calls are blocked. Therefore, the blocking probability is running from n minus g to n p suffix n, that will be the blocking probability. If we made the summation over the steady state probability which we got it in the previous slide, substitute those things. So, that will be the blocking probability. Now, I am moving into extending the same logic into 3G wireless networks. So, here also we are making a model for only one cell, and not only one type of calls, we have three types of calls. One is the voice call, the second one is the video call, and the third one is the data call. In the 2G networks, we have only one type of call, that is a voice call, and the voice calls are subdivided into two types, handoff calls and the new calls. So, here also the voice calls are divided into new calls and handoff calls, because we are considering a performance model for a one cell, and the calls could be a voice call, could be a new call or the handoff calls. The video calls, again we are dividing into two types. One is the hard QoS video 1 type call, and the soft QoS, that is video 2 calls, because there are some video calls, it is a hard QoS, that means it will not tolerate the delay, the video conferencing live program and so on. So, that type of video calls are the video 1, whereas the video on demand, that can tolerate the delay. So, that type of call is called the soft QoS calls. So, this is a video call, that type is called the video 2. Then the last data traffic, that also can be classified into new call and handoff calls. So, here the priority is the voice calls are the higher priority, then the video 1 call, then video 2, then the data. So, the way we have discussed the 2G cellular networks, we are extending the same idea into 3G wireless networks with the three types of calls with this priority, and the priority is taken care with the fixed guard channel policy. Earlier we have only one voice type call, now we have three types of calls. Therefore, the reservation also changes accordingly. And instead of only one voice call, we have 3 types of, therefore the number of channels allocated to different calls also changes. So in this scenario we have taken voice calls uses only one channel, whereas the video calls that needs more bandwidth, therefore assumption, we have made an assumption 4 channels are needed for the video calls, and the data traffic needs only one channel. Therefore voice and so this is explained in this paper in detail. So here we made the assumption the call arrivals Poisson process. The usual way is 2G networks call arrivals are Poisson process, call holding times are exponential distribution, and so on. But what we are making the extending the model with the one channel is needed for voice and data traffic, and the 4 channels are needed for the video 1 and 2 traffic, and the priority is voice, then video 1, then video 2, and data. And since the priority is there, we are reserving a HI number of channels for the handoff calls in this order, and the NI channels are reserved for the new calls of voice and video 1 and 2, and there is no reservation for the new data traffic calls. And we allow the retry of the calls of a new voice and the video 2 and the data traffic. Therefore, the proposed model, instead of a Poisson, we have a Markov arrival process for the data arrival, and instead of exponential distribution we have more general situation, that is a phase type distribution for the holding time, call holding time. And whenever the calls that are blocked, it can go to the orbit and it can retry, and the retrial times also assumed to be a Poisson distribution. And since we have made the reservation for the calls with the HIs and NIs, accordingly these total number of channels are divided into many parts, and the calls will be allotted according to this priority. That means from 0 to M7 the handoff voice will be allotted from 0 to M, whereas the new voice will be allotted till the number of busy channels going from 0 to M7, because H1 is a reservation for the handoff voice call. So like that this is the higher priority, then next priority and next priority and so on, and this is the new data call, and there is no priority for the new data. Therefore this is the lowest priority call traffic, and this is the corresponding queuing model. You can compare the queuing model of the 2G networks with the 3G networks. Since we have 3 types of calls, that is voice, video 1, video 2 and data traffic. So we have a different traffic is contenting for the channels in the channel pool, and after the calls are over, then it will either be completed within the cell or hand off to the neighbor cells. The first one is the handoff voice. So the call admission control scheme allows, then the call will be allotted, otherwise it will be dropped. There is no waiting, there is no orbit, the calls blocked won't go to the orbit and wait. Whereas the new voice call, if there is no channel, then it will go to the orbit with some probability, it will again retry after phase type distributed time, which we have made the assumption, otherwise it will quit with the 1 minus this probability. Similarly for the handoff video 1, either it will be accepted or it will be dropped, whereas the new video 1 also, either it is we use the word dropped for the handoff and the blocking for the new type new calls. Therefore new video 1 call will be blocked if there is no bandwidth, whereas the video 2, if there is no bandwidth, then it will go to orbit with some probability it will come back, with 1 minus of this probability it will quit. Similarly the new video 2 also, either it will get accepted if the channel is available, the required number of channels are available, otherwise it goes to the orbit and retry. the third type, that is a data, both the new and the handoff data, either it will be accepted or it will go to orbit and come back. So, it is similar to video too, but the difference is the video takes 4 channels at a time, whereas the data and the voice takes only 1 channel at a time. So, this is the corresponding queuing model for the 3G wireless networks, cellular networks for only one cell. So, here the stochastic process is the state of the cell. What is the number of channels are available at that time t, that is going to be the stochastic process over the time, and this will be modeled as a quasi birth death process, whereas the 2G wireless cellular networks is we modeled as a birth death process. So, here this is a quasi birth death process. So, what is the meaning of quasi birth death process? This is a generalization of birth death process. Here the Markov chain with the state space S, and the state space can be divided into k levels, and each level you have a capital M states or M phases. Suppose you have a M capital M phases and we have a k levels in it. So, it is a generalization of birth death process, means suppose the system is in some ith level and some state, then there is a possibility it can go to the I minus 1th level with the different states, or I plus 1th level in the different states, and so on. Therefore, here the state space is divided into k levels, and each level has the some finite number of, need not be the same number, each level should have some finite number of states. So, it is a generalization of birth death process. Accordingly, you have a state space with this type of vector, and you can study in detail in the particular paper about how to obtain the performance measures. And here I am listing what is the meaning of I, J, K, L, and what is the meaning of US, and what is the meaning of S suffix, and so on. And the last one, what is the meaning of RL, means the phase of retrial of calls in orbit. So, here also we uses the difference between the birth death process and the quasi birth death process. The Q matrix consists of block matrices, whereas in the birth death process the Q matrix is a tridiagonal matrix, and each entries are the elements, whereas here each entries are the matrix, and the elements of that matrix also again will be a matrix based on the number of levels. And in this model we have a 4 level quasi birth death process. Therefore, we have a Q matrix with the block matrices in 4 levels, and the 4th level you have the matrix with the entries are the elements. I am just skipping this part of how the generator matrix, each element, each matrix exists. And our interest is to get the steady state distribution for the quasi birth death process also. So, here I am making the assumption the quasi birth death process is ergodic, therefore, the steady state distribution exists. This is a generalization of birth death process, therefore, the Markov chain, whatever the steady state distribution condition you need, the same condition you can cross check. So, here this QBD is ergodic, therefore, a steady state distribution exists. Then you can solve the x times Q matrix equal to 0 with the x times E vector that is equal to 1, using that you can get the steady state probability vector. And since it is a QBD, you can use the matrix geometric technique, that is a well known technique for the QBD. We can use that and get the steady state probabilities. And these are all the, once you know the steady state probability, you can get the blocking and the dropping probabilities. Since we have 3 types of calls, we can analyze the blocking and the dropping probabilities for the various traffic, and also we are discussing the retrial and orbit and so on. So we can find out the probability that the new voice handoff video to new video to handoff data and the new data calls join orbit. What's the probability for that? You can find out after getting the steady state probabilities. So one can see the paper to understand the complete paper. And also one can discuss the special cases by making the simpler assumptions. The last assumption is a Poisson arrival exponential service and no trial, and one type of call that will end up into the 2G cellular networks which we have got it. So if you make a subsequent special cases, you will end up with the blocking probability and the dropping probability which we have discussed in the second generation cellular networks.